Okay, let's have a look at these two sequences here. We've got the first sequence is an is defined as e to the power of n, and then we've got bn is just n to the power of n. And of course, as n goes to infinity, both of these sequences are also going to go to infinity. And what we're interested in here is which of these sequences actually grows to infinity at a faster rate. So just to start with, e to the power of n, so it's really clear. This means e to the power of n, and then you raise e to the power of that. So this isn't the same thing as e to the power of e to the power of n. So this is what the notation means. We don't want this. If we did have e to the power of n, like this here, then this would just be some number to the power of n, and then n to the power of n. Once n is bigger than e to the power of e, your bn would be bigger than this. So bn would definitely win in this case, but we're not so interested in this case because what we need is actually e to the power of, and then in brackets, e to the power of n. Okay, so let's start by comparing these then. So what I'll actually do is I'll start with bn. So here, bn, this is equal to n to the power of n. And then what I'm going to do so that I can make a comparison between this and an here is I'm going to write this as e to the power of log, natural logarithm, n to the power of n. And then using the laws of logarithms here, you can take the power outside. So you get this is equal to e to the power of n log n. So bn is this. And then we're trying to compare this to an, which is e to the power of n. And hopefully you can see here, because we've got e raised to the power of something and then e raised to the power of another thing, all we really need to do now is compare n log n with e to the power of n. See which one of these grows at a faster rate. Okay, so, well, first of all, we'll start with e to the power of n and just write this using the Taylor expansion at 0, or your series definition of it, and so on. So you've got all these different terms. E to the power of n is defined as this infinite sum. So let's compare this with the n term here. Well, actually we've got an n squared over 2 factorial term here, so this thing is definitely going to grow to infinity much, much bigger than n. And then we've added a load of positive stuff to that as well in e to the n, so this term is definitely bigger than n. But then we've still got this log n term to deal with. And what I'll do just as an aside here is we'll show that log n, this actually grows to infinity slower than just n. So let's have a look at the limit as n goes to infinity, this ratio. So if log n grows to infinity slower than n, then hopefully this limit will be equal to 0. And we can use L'Hopital's rule here. So you've got this numerator here, log n converges to infinity, so does n. So you can use L'Hopital. You'll get differentiate log n, this gives you 1 over n, and then differentiate n here, you just get 1. So this is the limit as n goes to infinity of just 1 over n. Of course, this is equal to 0. So log n grows to infinity slower than n. So let's say log n is less than or equal to n, basically for all large enough n. And then a consequence of this, because we're interested in n log n, we just multiply both sides of this by n. So n log n is less than or equal to n squared for all large enough n. And that's quite nice, because then, well, we're interested in bn, we want this n log n term, we want to compare this to e to the power of n. We know this thing is basically, it's going to be less than or equal to n squared. So let's compare our n squared now with just this one term, this n cubed over 3 factorial term in e to the n. So e to the n, this is much, much bigger than n cubed over 3 factorial. And then this, of course, is bigger than n squared a large enough n. So actually, for any values of n over a certain threshold, n has to be greater than or equal to 6. This will be greater than or equal to n squared. Then we know that this is bigger than n log n. But actually, e to the power n is much, much bigger than this, because e to the n you could say is bigger than n to the power of 4 over 4 factorial. And basically here, it's not just an inequality, but you can say that e to the power of n grows to infinity at a much, much faster rate than n cubed, which grows to infinity at a much, much faster rate than n squared, which grows to infinity at a much faster rate than n log n. So what we can conclude there then is, thinking back to what were we dealing with, we're dealing with bn, which is e to this n log n, and we're also comparing that to an, which is e to the power of e to the power of n. Well, this one grows much faster. So we can conclude here then that an is the winner, which I think is quite nice. It's quite an interesting example here. You've got e to the power of e to the power of n. So you've got a small number to the power of a small number to the power of n, where n is big. Whereas for bn, you've got a big number to the power of a big number. And if you write an in this form with e to the power of e to the power of n, what you've got is something small to the power of something really, really big. And if you want to compare this to something big to the power of something also big, what you'll find is, as a general rule of thumb, the exponent, this e to the power of n, if your power is much, much bigger, generally that may well give you a bigger number, although it would depend just how small your small thing is there. Okay, so which sequence grows faster as n goes to infinity? An does by quite a large margin here. So an is e to the power of e to the power of n, whereas bn is just e to the power of n log n, and e to the power of n grows much, much quicker to infinity than n log n.